So we're going to ideally finish chapter 5 today and then move on into the beginnings of chapter 6, either at the end of today or early next time. First, some things about our weekly work habits reminder, the Try Hard Tuesday. So one thing about that comes up a lot this time of the year is, how should I get help from behind? How do I get my questions answered? I didn't do as well on the exams I wanted to, and so on. I mean, office hours is certainly one way to do that. A lot of people in the class this size, they worry that, like, oh, it'll be too crowded, there'll be too many students there. But I would estimate there's only like 5 students at the most that have even attended office hours more than once. Most Thursdays, especially, I'm just kind of sitting there. So don't use that as an excuse if you're able to and want to. It is a good way to get caught up on some things. Some suggestions on how to best use the time. This is what a lot of students do, especially those that are very successful in this course. So as you're doing all of your different homework attempts, quizzes, practice problems, and so on, if you keep your work organized in a notebook, um, you can bring that with you and then kind of keep track of the questions and topics you don't understand, even if you got it correct, because sometimes it's easy to um, you'll look back at your results from a homework assignment like, oh, I got that question right. I must know how to do it. But at the time you were doing it, you may have had something you were confused about. So make sure you keep track of all that. Don't just assume that because you got it correct that you understood it fully. And then if you bring that information to office hours, it's really a lot easier for me to sort of see how you approach the problem and identify what you aren't understanding. A lot of times I'll get questions by email, which is fine, where students are like, I don't know how to do this one. But it's more effective if you're able to come in person and effectively communicate with me what you did, kind of show me your work a little bit, and then usually we can kind of get to the bottom of what you might be missing. So I don't claim to be like a chemistry whisperer or anything, but I can usually tell just by talking one-on-one and by looking at the steps that you've taken to solve a problem where exactly you went wrong. It's a lot more effective that way in many cases. So that's my suggestion. If you're going to start coming to office hours, you're welcome to, of course, and you can use the time effectively by bringing work with you that some things you've already done and kind of keep track of the steps that you may have had problems with. Okay, so with that though, we're going to move back into the material. And what we're going to start with are just several examples of stoichiometry problems. So we kind of ended last time with outlining the general concept for how stoichiometry works. We gave one example problem, um, and then kind of had ended there. So we're just to get reoriented and see the different variations. Let's talk about how this would work. So the first thing is, in many stoichiometry problems you're going to be doing, you're not going to be given directly the balanced chemical equation. That's something that you're going to have to come up with on your own. So if you have problems set up like this is iron metal reacts with water to form magnetite. So this is another iron oxide compound, but different than rust. And it forms hydrogen gas also. How many grams of water are required to react completely with 25 grams of iron? So in a problem like this, you're not given a balanced chemical equation or even any sort of chemical equation. So that's really going to be your first starting point. You can't approach any stoichiometry problem without a balanced equation. So that's the first thing we're going to do. So we have to use here words translated into an equation. So iron metal, which is just Fe by itself. So any elemental metal by itself is just the element. Um, and it's going to react with water. We should hopefully know that water is H2O. And then the two products are what we call magnetite here, but the formula for that is Fe3O4. And then hydrogen, H2. Which at this point you may not realize hydrogen is H2, but it is. We'll get to that later on in the course. All right, so those are the reactants and products. Now we have to put coefficients in. As we kind of discussed last time, setting the most complicated thing to 1 is usually helpful. So we'll throw a coefficient of 1 there or imply that it's 1 and not touch it. So we have 3 irons in the product, so we'll need a coefficient of 3 there. We have 4 oxygens in the product, so we're going to set oxygen next. We have 4 here in Fe3O4, so we need a coefficient of 4 in front of water to have 4 oxygens on both sides. And then for H2, we'll do that last. So over here on the left, we now have 4 waters, which would be a total of 8 hydrogens. H2 has 2, so we need also 4 of those to balance. As I said before, if you're balancing an equation and you have time, you may want to check yourself by making sure that the number of elements of each type on the reaction product side are the same. You don't always have time to do this, but it's good as you're first learning it, especially. So here we have 3 elements involved. iron, hydrogen, and oxygen. On the reactant side, we have 3 Fe, so 3 times 1 is 3 of those. On the product side, we have a coefficient of 1 here, but 3 iron atoms in the formula. So 1 times 3 is also 3, so that one checks out. For hydrogen, we have 4 waters on the left. Each water has 2 hydrogens in the formula, so there's a total of 8. And on the right, we have 4 H2s, also with 2 hydrogens each, so a total of 8 there as well. And then for oxygen, we have 4 waters with 1 hydrogen atom, one oxygen atom in the formula is a total of 4. And then we have 1 Fe3O4, 1 equivalent with 4 in the formula, also gets 4. All right, so that one wasn't too bad to balance, but you're going to want to get proficient at balancing equations because in a stoichiometry problem, that's the first step. We didn't really even accomplish anything that this was asking yet. We're looking for how much water is required to react with 25 grams of iron. We haven't even started that yet, but we do need the balance equation to get that. Okay, so now we can go forward and do the steps that we need. So reminding ourselves of the balance equation that we just came up with. Now, it turns out in this case, we don't even really care about the product side because we're looking for amounts of the two reactants, iron and water. So what we're looking for here is how many grams of water. So we want to write out what we're trying to find. And our starting point is going to be the mass of iron, which is 25.0 grams. So this is how I always like to start. Write out what you're looking for, write out what you're given, and then figure out the path that's going to take you from one to the other. In a stoichiometry problem, your first step is going to always be to convert to moles because all of these ratios in the balanced equation are mole ratios. So in this case, we need the atomic mass of iron. We want grams in the denominator to cancel out, so we're going to put the atomic mass in the denominator. So we'll switch over to the periodic table. Fe is right here, number 26, in the middle of the D block, and its atomic mass is 55.85. That's that number there. Okay, so that's going to be the molar mass or atomic mass of iron, so we'll use that to convert it into moles. And then once we convert into moles of any substance, we can convert into moles of any other substance in the equation by using the balance coefficients. So we're in moles of iron. We want to get into the amount of water. So we're going to look at mole ratio of water over iron. We want iron in the bottom so that it cancels out. And if we look at the coefficients that are there, iron has a coefficient of 3. Water has a coefficient of 4. So we're going to multiply by 4 over 3. 4 moles of water for every 3 moles of iron. That cancels out and gets us into moles of water. Writing out units is critical because we need to know when to stop. So this is moles of water, but we're looking for grams of water. So we have one more step, which I'm going to put on the next line here, which is going to be to convert moles back into grams. That's going to be using the molar mass of water. This time multiplying by it so that moles cancel out. And the molar mass of water is going to be 16 from oxygen plus 2 from hydrogen, so roughly 18.02 if you'd like to be more exact. So 18.02 grams of water in 1 mole. That's the molar mass of H2O. And that's the last step here because now we have grams of water, which is what we're looking for. So we just multiply across. All right, in a typical problem in WebAssign, you would just be entering the number, but we want to make sure we always keep track of units when we're doing this so that we know what exact quantity we're referring to and what conversions are going to relate those to each other. All right, so any questions on that? Pretty standard mass-to-mass stoichiometry problem. And then this one is a very similar variation on that. We want to know how many grams of hydrogen are formed during the reaction of 25 grams of iron. So whenever you're doing stoichiometry, you can relate amounts of any two substances that are in the balanced equation, any two reactants, any two products, whatever the story might be. So we're going to have the same balanced equation here. So that we don't have to work out again. And then this time, the only difference is that we're going to start with the mass of iron that's reacting and then calculate how much H2 would form from that. So it's a very similar set of conversions, but just one different substance involved, which is hydrogen in this case. So the first step is the same. We start with the amount of iron that we're given. convert that into moles using its atomic mass. And then from here, once we have moles of one substance, we can convert to moles of any other substance using the coefficients. So we want to convert into moles of hydrogen and have moles of iron cancel out. So we're going to put it in this way. We look at the coefficients, iron and H2. So H2 has a coefficient of 4. Fe, iron has a coefficient of 3. So this time we're going to multiply by 4 over 3. Actually, the same ratio we'd used last time. Yep, same ratio, but two different substances. But then this time we're looking for the mass of H2, so we need to use the molar mass of that substance to convert back into grams. So the molar mass of hydrogen is 2.02 grams per mole, two hydrogens. So it's just that multiplied by 2. So the atomic mass of hydrogen is 1.01. 2 times that is 2.02. So sorry, H2 is in the bottom here. I messed up here, sorry. All right, so that cancels out moles and gets us into grams. So it's a much smaller number this time because the molar mass is smaller, but it's 1.21 grams of H2. Okay, so those were a couple of typical stoichiometry problems, mass to mass. We start with mass of one substance, calculate mass of another. That's kind of the standard for this chapter. All right, any questions before I move on? Now, yeah, sorry. So in terms of significant figures, basically, if you have if you report your answer to the correct number of significant figures, I'll make sure it doesn't get marked wrong, obviously. That said, unless it's a problem specifically about significant figures, which only is going to occur on the first exam or the final, because that's the review chapter topics, any other numerical problem you do, WebAssign likely won't, I shouldn't care about how many significant figures you have. So I would just say don't do too much rounding, but it's helpful to look at what's in the problem. So if all your numbers in the problem have 3 sig figs, make sure you report your answer to ideally 3 sig figs, and then you won't have to worry about rounding too much. If you chop it off too much, if you round to only 1 or 2 significant figures, you run the risk of your answer then being outside of the acceptable range. So I would just say don't do too much rounding. I won't mark you wrong if you have the correct number of sig figs, and for some reason it does. But typically, if you follow the rules, or even if you're a little bit more precise than you need to be, even carrying 1 extra, it's not going to care, and it's not going to mark your answer wrong for that reason. All right, so the next topic we need to cover in stoichiometry is called limiting reactant. And so before I kind of jump into it, you can kind of think about this almost like I don't know if anybody here bakes, I don't, but let's say you're a baker and you're trying to make a loaf of bread that requires 2 cups of flour, 3 eggs, and what else you put? I don't know what else you put in bread, but anyway, a tablespoon of yeast, right? So let's say that's what you're trying to do, and then you look in your cabinet and you want to make a bunch of this, but you have 5 cups of flour, 4 eggs, 3 tablespoons of yeast. So basically, you have to figure out like, well, what's the maximum number of loaves of bread I can make while keeping that ratio correct, right? And that's exactly what limiting reactant is. So sometimes when you do a chemical reaction, you're mixing 2 or more reactants together, and they may not be in exactly the right proportion to fully react with each other. So you're going to have some that's left over of 1 or more of those. So that's what's called your excess reactant. So limiting reactant is the one that's going to be reacting completely. It's the one that's going to determine how much of the product you can form. So that's the idea of limiting reactant. You don't always have things present in the perfect stoichiometric ratio, which means you're going to have something that gets reacted completely and then something that's going to be left over in many cases. So there's sort of 2 ways of doing this, or probably more than 2 in reality, but I'm going to cover both of them, but the one that I'm going to use is the way that I was taught, which I think has some advantages to it. Both of them kind of, I would say, are similar in terms of the amount of work you do, the amount of time that it takes to use these approaches, but I I think the way that I do it requires less thought, which is always helpful. All right, so here's the way that the book does it, and it does require you to think a little bit. So the book says, okay, let's determine you have two reactants where you're given amounts of both of them. So you're going to determine the moles of each. So I'll call the two reactants A and B. We're going to determine the moles of each of them. Then what you're going to do is using stoichiometry, you're going to calculate or determine how many moles of B are required to react with that much A. But here's where you have to really like think about this clearly. And to be honest, even I trip myself up sometimes when I think about this. So we're calculating how many moles of B are required to react with that much A. If the amount that you calculate is less than the actual amount, so meaning you don't need as much B as you have, that means A has to be limiting reactant or vice versa. So again, this is where you have to think about it clearly, and why I don't really prefer this approach, because it's easy to get yourself tripped up and think about this backwards. So if the amount that you calculate of B is less than the actual amount that's present in the reaction, that means you have more B than you actually need. That tells you that A has to be limiting reactant. And then the opposite would be true in the other case. Or the other way you'll sometimes see the problem done is if you're calculating an amount of product that forms, you basically do the problem twice. You have, okay, this much A, this much B. Let's calculate how much product forms from A. Let's calculate how much product forms from B. The lesser of those two amounts has to be the correct one, and that would identify your limiting reaction that way. But it's basically involves doing the problem twice and using a lot of thought to keep track of what your limiting reactant is. So the way that I do it, which I was taught when I was back at your educational level, taking college chemistry for the first time, is a one that doesn't require you to really do much thought. It's just for every problem that involves limiting reactants, you're going to do the same series of steps at the beginning. That will easily allow you to identify what the limiting reactant is. And then any other calculations you do involving stoichiometry are going to start with that reactant. And the other one you don't really have to worry about necessarily. Okay. So here's what we're going to do. We're going to determine what's called the stoichiometric ratio for each reactant. As we'll kind of formalize and get to here in a second, the way that you have to know that you even need to worry about limiting reactant is if we give you amounts of two or more reactants. If you know how many grams of two reactants you have, or in chapter 6, other amounts that you can use to calculate moles, then you know you have to figure out which one's limiting reactant to be able to get the problem right. So what we're going to do is for each reactant where we know the amount that we have, we're going to determine what's called the stoichiometric ratio. And that's going to be defined as the moles of that reactant. So we're still going to have to calculate the moles of each reactant. Always a good place to start anyway. Then we're going to divide that by the reaction coefficient, the coefficient from the balance equation for that reactant. So we're going to get this ratio. And basically what turns out to be the case then is that if you calculate this ratio for all the reactants, the reactant with the smallest stoichiometric ratio is your limiting reactant. Now, the caveat of this method, and the place where sometimes it throws people off, is to recognize that once you figure out what the limiting reactant is, this stoichiometric ratio is effectively a useless quantity. Its only purpose is to tell you what the limiting reactant is. But then from there, you have to still do all the calculations. And so what you have to recognize then is we still have to go forward, and any subsequent calculation we do involving how much product forms or how much of the other reactant is left over, whatever the case is, any subsequent stoichiometric calculation will start with the limiting reactant. Now, you've already calculated moles of limiting reactant as part of this. That'll typically be where we go back to. But you don't want to use the stoichiometric ratio for anything other than figuring out what your limiting reactant is. But as I said, it's nice because you just do the same series of steps for each reactant, and all you have to do is pick the smaller number, so it doesn't require a ton of thought at all. Versus, okay, I'm going to calculate the moles of each. Then is this mole smaller than that mole? That's no, it's just like that. The previous method I covered, I think, is just too much. You can take a picture, whatever you want. Yeah, in this class, I should say. All right, so uh, all right, so then we're gonna go forward with that, and that's how I'm typically gonna approach it. But of course, as I kind of already mentioned, a common question that also comes up is, how do I know if I even need to worry about this? Because we just did a bunch of stoichiometry problems at the beginning of today where I didn't care what the limiting reactant was. I didn't tell you or have to find it out or anything like that. The way that you know this is you look at the problem as you're starting it, and if you're given exact amounts, precise amounts of two or more different reactants, you have to figure out which of those is a limiting reactant. Typically in this course, it won't be more than two, but it could be more. But if you're given amounts of two or more, before you start the problem, you must first determine which of those is a limiting reactant. In this chapter, it'll mostly be grams, or so okay, this many grams of A, this many grams of B, or maybe this many molecules or this many atoms, something like that. The registers you learn. But as we go forward and talk about stoichiometry in other contexts, if you have any amount of substance given where you can use that to determine the number of moles of that substance, you have to figure out which of those is a limiting reactant to be able to approach the problem correctly. Now, what sometimes happens is you'll be given an amount like we saw in the problems we did today. If you're only given an amount of one substance, so in the two practice problems we did earlier, we told you how much iron you're reacting, but we didn't tell you anything about anything else to start with. So if you're only given an amount for only one reactant, or if the problem starts with a product amount, if we say, well, we're forming this much product, how much reactant do you need? In which case you don't know the amounts of any of the reactants. But if those are the situations, if we're not giving you the amounts of two or more reactants, only one or zero, then you can just start the problem. You don't have to worry about what the limiting reactant is, because in that case, it doesn't matter. Right? Because to basically use the terminology we're now going to start using, if we only give you the amounts of one reactant, if we say you have, like we did in the first problem today, we have 25 grams of iron, our assumption then is that any other reactant would be present in excess. So the one, if you're only given the amount of one reactant, you assume that that's your limiting reactant. Everything else would be an excess reactant. But in situations where we give you the amounts of two or more, then you have to first figure out which of those is the limiting reactant before you start going crazy with stoichiometry. So let's see how that works in a few example problems and what we can sort of now do with this. Okay, so here I gave you the balance equation for the reaction of ammonia with fluorine. And we want to know how many grams of N2F4 can be obtained from the reaction of 5 grams of NH3 with 15 grams of F2. So in this case here, we should see that there's a dead giveaway for this being a limiting reactant problem, because our two reactants are NH3 and F2, and we tell you that we're mixing together 5 grams of NH3 and 15 grams of F2. And we don't want to assume that that's the perfect 2-to-5 ratio that they're going to react fully. That means there could be possibly and likely that you don't have the exact right ratio of these. One of them is going to limit how much of the product forms. The other one's going to have some left over. So the first question is how many grams of the product are obtained. So as I said, typically the way we'll approach these problems, way that I like to, and you're welcome to adopt this approach if it works for you, is for each reactant, we're going to determine what's called the stoichiometric ratio, which means we find the moles of that reactant and then we divide it by the coefficient. So let's go through that first. This might feel like it's extra work, but then it's nice because you'll not immediately, but you'll eventually know what the limiting reactant is, and then you'll move forward from there without any hesitation. So we're going to determine the moles of each reactant first. That's going to be part of the process of getting the stoichiometric ratio. But then once we have that amount, we can still use it for subsequent calculations. So it's not necessarily totally wasted effort either. So for NH3, we're told that we have 5 grams. And the molecular weight, MW, is as is abbreviated, is 17.0. So 1 mole of NH3 has a mass of 17.0 grams. So we need to get really good at these mass to mole conversions for this part of the course. So it comes out to 0.294. All right, so that's the number of moles of NH3. We're going to do the same thing for the other reactant, which is F2. For that one, we have 15 grams, 15.0. And then 1 mole of F2 has a mass of 38.0, 2 times the atomic mass of fluorine. But that's given to you here, so we don't have to calculate it. So we get 0.395. Now again, though, we can't stop. Remember the way that we determine limiting reactant is we take now the moles of each and divide it by the coefficient. We can't just say, oh, there's fewer number of moles of NH3, that has to be our limiting reactant. It's not quite that simple. So the second step to do this is we're going to divide by the coefficient to determine the stoichiometric ratio. So for ammonia, NH3, we take the moles of ammonia, which is 0.294. Don't really need units here. We'll just put the numbers in. And we're going to divide that by the coefficient. In the balanced chemical equation, the coefficient in front of NH3 is a 2, so we're going to divide by that. And that comes out to 0.147. Then we're going to do the same thing for F2. The number of moles that we got for F2 was 0.395. And the coefficient for F2 in the balanced equation is a 5. So we divide those two, we get 0.079. All right. And now the smaller of these two stoichiometric ratios is going to be the one that's limiting reactant. So this number here is the smaller of the two. And so that's going to be our limiting reactant. So F2 is identified as limiting reactant. And I chose the numbers I did for this problem to illustrate 2 key points and not to tempt you into making shortcuts or to making assumptions. One is that you notice that we have 3 times as much mass of F2 as we do NH3. And we have more moles of F2 than NH3, but F2 is still a limiting reactant. So you really have to go through all these steps. You have to calculate the number of moles and divide by the coefficient. If you try to cut corners in any way and make assumptions based on just the grams of each you have and the number of moles you often will be led astray. So it's that ratio that really helps you determine, not the number of grams and not even the number of moles by itself. Okay. But now that we know F2 is a limiting reactant, and you'll get really good and fast at doing that, then we can go forward and do the calculations. So now we want to calculate the grams of N2F4 that can form. So the third step in this is going to be to just do the calculation. But we always have to start the calculation with the limiting reactant, which is F2. So we're looking for grams of dinitrogen tetrafluoride. We could go all the way back to the beginning and start with the mass of F2, although our first step is going to be convert that to moles, which we already did once. So we can save ourselves a little bit of time by recognizing that we calculated that there's 0.395 moles of F2 in the previous steps. So we already have that number. So we can actually just start there and move forward without having to do the other step over again. Now we're going to use coefficients from the balanced equation. We want moles of F2 to cancel. We're trying to find how much N2F4 that would produce. So that's going to be in the top here. N2F4 has no coefficient in front of it, which means it's a coefficient of 1. F2, as we already saw, has a coefficient of 5. So that's moles of N2F4, and then finally to get into grams, we have to just multiply by its molar mass. The molar mass of N2F4 is 104. 104.0 grams per mole. So that cancels out moles. So we multiply that across and we get 8.22. If you had started with the wrong limiting reactant, if you had started with NH3 instead, you would have gotten a number that's bigger than this and also not correct because you don't have enough fluorine to form more than 8.22 grams. So fluorine limits how much of the product you can form, which in this case is 8.22 grams. All right, questions on that? All right, now once we have that, the other thing that we can then do in a limiting reaction problem is figure out, well, how much of the ones that aren't limiting are left over. We call that excess reactant. So whatever reactant is not the limiting reactant is called the excess reactant or reactants. And so in this case, if F2 is a limiting reactant, NH3 is an excess. And this is what the question is asking, is how much of that is left over? So how many grams of excess reactant remain? NH3 is the excess because it's the one that's not limiting. So the way we do this problem is sort of in two steps. We do it by difference. First, we're going to use stoichiometry to figure out how much of the NH3 actually reacts with the fluorine that we have, the F2 that we have. And then we're going to subtract to figure out how much is left over. So we're going to do a calculation to figure out the grams of NH3 that are consumed in the reaction. And that's just a stoichiometry calculation. So we go back and start with moles of limiting reactant is 0.395. Remember, any calculation we do, any stoichiometric calculation we do, once we've identified the limiting reactant, has to start with that substance. So we're starting with moles of F2 again. We can calculate the grams of NH3 that react with that. So we want this ratio here so that moles of F2 cancels. The coefficient in front of NH3 is a 2. The coefficient in front of F2, as we've already seen, is a 5. That's moles of NH3, and then we multiply that by its molar mass, 17.0, to figure out what mass of NH3 that corresponds to. All right, so that's 2.69 grams. And that, again, represents the amount of NH3 that was consumed during the reaction. How much reacts with the 15.0 grams or 0.395 moles of limiting reactant we actually have. So the rest of the NH3 is going to be the excess, the leftover, and we just get that by subtraction. So we didn't have it here, but at the beginning of the problem, we said that there was 5 grams of NH3 put in. So that's our starting amount. $2.69 grams reacted, as we just calculated. So that difference is 2.31. So we had almost twice as much NH3 as we actually need. Almost half of it would be then left over. Okay, so if you're asking for how much excess reactant there is, it is one simple extra step, which is after you calculate the mass or whatever amount of that reactant was consumed, you have to subtract it from the original amount to figure out how much is left over. So that's the only additional wrinkle then that these sort of bring to us. Any questions on that? All right, since this is such an important topic, I do want to give a couple more example problems. So let's go through a more complicated situation now where we have 3 reactants and we're given the amounts of all 3. So it's this complicated reaction here. Actually, this substance here, which this is called sodium azide. We didn't really learn about what the name of that anion is, but N3- is azide. That's the substance that's used in airbags. So if you hit it with a hammer or hit it with a large shock, it'll explode. That's how you inflate your airbags very quickly. It releases nitrogen gas, basically. That's a fun substance, but I wouldn't recommend playing with it too much. And so we have it is shock sensitive. It's safe otherwise, but don't hit it with a hammer unless you want to see a boom. All right, so we have But here, the situation though is we're forming that as one of our products, but we're telling you that we have 5.25 grams of N2O, 4.05 grams of sodium, and 2.57 grams of NH3 combined. So we have amounts of three substances given. We're mixing three things together, and we're giving you exact gram amounts of all three. So clearly, we have to go through the steps of finding out what the limiting reactant is, and this time we have to do it for three different substances instead of two. So it's slightly more complicated. But we're going to follow the same set of steps for all three. We're going to calculate the moles of each using their molar mass, and then we're going to divide by the coefficient to get the stoichiometric ratio. So for the first reactant is N2O. We have 5.25 grams of that. And we were nice here and gave you all the molar masses, molecular weights, so you don't have to calculate them. So we have 44.01 grams of N2O in 1 mole. So we have 0.119 moles of N2O. 2O. And the stoichiometric ratio then for that is that number divided by the coefficient for N2O, which is a 3. And I'll just keep it 2 sig figs. We don't need too many here to compare. So it's about 0.04. All right, so that's the stoichiometric ratio for N2O. We just have to do that 2 more times for the other two. So we have sodium as one of the other reactants. We have 4.05 grams of that. So for sodium, it's just going to be the atomic mass, which we gave you here, so you don't have to look it up. That number's off the periodic table because this is an element. So 1 mole of sodium has a mass of 22.99 grams. So we have 0.176 moles of sodium. And the stoichiometric ratio for that is going to be that number. And its coefficient is 4. So it's not too different, but it's a little bit bigger, 0.044 in this case. So a little bit bigger than the first one. So we know that sodium is not the limiting reactant. And then last time now for NH3, figure out its stoichiometric ratio. We're starting with 2.57 grams of NH3. We already saw NH3 in the last problem, but its molar mass was given again here, 17. It's a little bit more precise this time, but same number, 17.0. So for NH3, we have 0.151 moles. And the stoichiometric ratio for that is that number divided by the coefficient, which is just a 1 for NH3. So clearly that number is the largest of the three. But to find limiting reactant, we just have to find which of those is the smallest. That's going to be N2O here has the smallest number. We didn't really ask for the number. It's not very meaningful by itself. But it does tell us that N2O is the limiting reactant, which is what this problem was asking for. Okay? So whether it's 2 reactants, 3 or more, I mean, I don't think it'll be more than 3, to be honest, in this course. But whatever the situation is, if you have amounts for 2 or more, you calculate that for all 3 of them, and that gives you limiting reactant. So any questions on that? That's the key step to doing this that I wanted to make sure we reviewed again. Then we want to know how many grams of NaN3, that sodium azide that we talked about as being a cool explosive compound, how many of those are theoretically obtained? So theoretically just means what's the amount that can form if all of the limiting reactant is consumed. So because we've identified N2O as limiting reactant, that's the amount we're going to start with. So whatever our limiting reactant is going to be the starting point for any future calculations we do. And this is just a typical mass-to-mass problem now where we're calculating the mass of sodium azide. And we're starting with N2O. We could either go back and start with the mass of N2O that we had, or as we said, we already calculated the moles of that, so we can just start there, save us a step. So we figured out that there's 0.119 moles of N2O. We want to convert into moles of the product, NaN3. So for that, we use the balanced coefficients. The reaction is balanced, so we have a coefficient of 1 in front of NaN3. N2O is a coefficient of 3, so it's going to be a 1 to 3 mole ratio. And then sodium azide has a molar mass of 65.01 grams. So we're going to multiply by that now to get it into grams of Na3. So this is moles, we want grams. So we're going to multiply by that number, which is the molar mass. All right, so that gets us grams of Na3, which is what we're looking for. So we stop there with a number of 2.58 grams. This one was multiple choice, which is, I guess, less common in the new homework system, but there would be your answer there. All right. So it is extra steps when you have to deal with limiting reactants, but it's unavoidable to have to do that. So any questions? Yeah. You don't need to ask permission. They're all online anyway, so not trying to hide anything. Okay. The last stoichiometry topic then that we need to cover is what's called yield. And there's sort of three terms that go together here. So sometimes when you're doing a reaction, ideally you figure out how much product should form and you kind of measure what the actual amount that you get is, and sometimes those two aren't exactly the same as each other. So what we would have then are again three different terms that are all related. So the first one is theoretical yield, and this is going to be the maximum amount of a product that can form when all of the limiting reactant is consumed. And that's basically what you would calculate using stoichiometry. So in the previous problem we just did, we calculated the mass of NaN3 that forms from the limiting reactant, and that would be what's called our theoretical yield. That amount can be calculated. So it's the maximum amount of product that can be attained if all of the limiting reactant is consumed. But if we were actually going to go in the lab and do that reaction, that's kind of a dangerous one. But if you go to lab, do any reaction, you would then collect your product in some way and measure how much of it you actually got. And those two numbers are not always the same. In most cases, they're not. So the actual yield is not one that you can calculate from first principles, but it would be an experimental number, the amount of product that's obtained experimentally. And I don't know how much synthesis or chemical reactions you guys do in your general chemistry lab. You'll get more of that if you take organic in the future, but there's in most cases the experimental actual yield is significantly smaller than the theoretical yield. Why would that be? Why is it not always perfect? Well, life's not always perfect. That's a general rule that you should get used to anyway. But in chemistry, why is it the case? So the first is that you can have just physical experimental losses. So you're running a reaction in a glass container, let's say, it forms the product as a powder, and you're trying to scrape out every little last fleck of that powder, and some of it just gets stuck to the walls. Kind of like when you're, scraping cookie batter out of using a baking analogy, scraping cookie batter out of a bowl, and like some of it just gets stuck to the side of the bowl, right? That's just inevitable. So that's what we would call experimental losses. So you're doing the reaction and your technique's not perfect, or just unavoidably sometimes you just lose some of your product. Sometimes you have a situation which is called side reactions. So that would be where either two of the reactants that are present can also react in some other way to form something else, so they don't all go towards forming that one product that you're looking for. Or sometimes the product forms and it can react with something else that's present in the reaction, another reactant or one of the other products that forms. Those are called side reactions. Basically, it's something that would happen that reduces the amount of product that can form. We're not going to talk about a lot, but I just want to be aware of that reason. And then the other one, which you'll cover a lot more in Chem 2, we won't really talk about it in this course, is a reaction that doesn't go to completion. So more formally, that's called an equilibrium, which is a topic that we don't cover in this class. But that's when you would have reactants going to products, but it doesn't go all the way to the product side. It stops where you have still a mixture of some reactants left that haven't reacted yet and some products, but it doesn't go 100% to completion. That's not as common in like synthetic reactions when you're trying to make something, but it does occur, and it's a topic you'll get a lot of in Chem 2. Really, like half of that course deals with that topic, so get ready for it. But for our purposes, what we need to be able to do is calculate the percent yield to understand how to use it. So once we have these two numbers, in a typical problem, you would calculate theoretical yield using stoichiometry. Actual yield will be given to you. And then the percent yield is the ratio of those two times 100. So actual divided by theoretical multiplied by 100. For our purposes, in a pencil and paper course, this should always be less than or equal to 100. You can't get a percent yield that's greater than 100%. In a lab, you might, and that just means that your product has some sort of contaminant in it. So you're measuring mass that's not just your product. But if for our purposes on pencil and paper type problems, you should get a number that's 100% or smaller in most cases, but never bigger. Okay, so that's what percent yield is. Now, the only other variation on this then would be if we give you the percent yield, you could solve for either the actual or theoretical yield if we have the other one. So it's, you might have to do some algebra sometimes, but this is the relationship. Percent yield is equal to actual over theoretical times 100, and you can use that in different ways. So we're going to go through just one pretty standard example then where we have this ugly looking substance here, tungsten 6 chloride, WCl6, can be prepared by the reaction of tungsten element with chlorine gas. So let's say we go in the lab and do this. We combine 5 grams of tungsten, 6.75 grams of chlorine, and at the end of the reaction, we measure 5.92 grams of WCl6 as a product. What is the percent yield for this reaction? So there's a lot going on here because we're giving you the amounts of both reactants, tungsten and chlorine, so we have to figure out which one is the limiting reactant. We're giving you an amount of the product forms. That's going to be our actual yield. So we need to calculate percent yield. So remember that percent yield is actual divided by theoretical multiplied by 100. Actual yield is already given to us here. So we don't have to do anything to calculate that. And that's typically the case because that number you can't really calculate. But we have to go through a stoichiometry problem to figure out first the theoretical yield. And then we'll be able to calculate percent yield after that. So we can't skip any steps. If we're calculating the theoretical yield as part of a problem like this, we have to write out the balanced equation, figure out the limiting reactant, and then do the calculation. So those same steps are always going to come up, and there's no real shortcut around them in most situations. So we have W reacting with Cl2 to form WCl6. We have 6 chlorines in the product, so we need a coefficient of 3 there. So simple reaction at least, just a 1:3 ratio of W to Cl2. But we're given masses of both reactants, tungsten and chlorine gas, so we have to figure out what the limiting reactant is. So we're first going to determine the limiting reactants so that we can calculate the theoretical yield of our product correctly. So we're going to calculate moles of each reactant. For tungsten W, it's 5 grams. So we're going to divide by its atomic mass in this case, which is given to us, but this is the number off the periodic table. It's just an element, so it's going to be 183.84. So we have 0.0272 moles of tungsten, and then the stoichiometric ratio for that would be that number divided by the coefficient. The coefficient for tungsten W is 1, so it's the same number. All right, so that's the stoichiometric ratio for tungsten. We do the same thing for the other reactant because we know the exact amount that we have. So for Cl2, we have 6.75 grams. The molar mass of Cl2 is just twice the atomic mass of chlorine, given here is 70.90. All right, so we have 0.0952 in this case. And then we have to find the stoichiometric ratio, though, to identify whether it's limiting or not. So it's that number. The coefficient for Cl2 is a 3. We had to write out the balance equation at the start, and then that's going to be 0.0317. All right, so again, not too different in terms of the numbers that we got, but this one is a little bit smaller, which tells us that W, tungsten, is the limiting reactant. So now we've identified tungsten as limiting reactant, we can calculate the theoretical yield of WCl6 using that as our starting point. So now we're going to calculate, we have the same balanced equation. And we're going to calculate the theoretical yield of WCl6. So that's just a stoichiometry problem. It has a fancy name now, theoretical yield, but we're just calculating the amount of that forms from the limiting reactant. So W is limiting reactant. We said that there's 0.272 moles of that. We calculated that on the previous page. So we don't have to calculate it again. And then the product forms in a 1-to-1 ratio with that reactant. Both of those have no coefficients, implied coefficients of 1. So that's a trivial step there. And then we just have to multiply by the molar mass of WCl6, given here is 396.54 per 1 mole of WCl6. So moles cancel out. So our theoretical yield is 10.8 grams of WCl6. And thankfully, that number is bigger than the actual yield. So that means we're at least on track. We didn't do anything completely wrong. So now we have actual yield here, theoretical yield that would just cancel. We're finally ready to calculate what it's asking for, which is the percent yield. So the last step is to calculate percent yield by just taking those two numbers and dividing them and multiplying by 100. All right, so the actual yield is given to us. That's the number that we actually obtain the reaction experimentally. We just finished calculating that the maximum amount is 10.8 grams. So what we get, keeping the rules of significant figures in mind, is 54.8% for that. All right, so that's a typical percent yield problem. Again, the only other really variations of this would be if we gave you the percent yield instead, you could solve for actual yield if it wasn't stated in the problem, but it's really this relationship here, using stoichiometry to calculate theoretical yield, actual yield often given to you, or if not, percent yield is given to you and you just solve for that. So there's some variation on this, but it's really one concept, and most of the legwork, most of the effort is the stoichiometry calculations. This is just one extra thing we can do at the end. All right, any questions on that? Okay, I believe that is the end of the chapter 5 material. So we're still in the unit 2 part of the course, so we're still not moving past what's going to be on the next exam just yet. But we are done with the first chapter on moles and stoichiometry, which again mostly dealt with mass to mass stoichiometry. We have this many grams of each substance, how many grams of the product forms, and so on, and then different terminology and concepts associated with that we covered today. What we're going to do in chapter 6 is move on to talk about chemistry that happens in solution. So when you have reactants that are dissolved in a liquid, typically water in our case, and different types of reactions that can happen, and then different ways of quantifying the amount of substance that would be in those solutions and doing stoichiometry from that as well. Now, just to give you a little bit of a heads up on this, I think the way I do it is more logical than the book, but you can disagree. So this chapter also has a lot of stoichiometry in it. So chapter 6 is dealing again with reactions in solution. So the stoichiometry aspects of that will be covered. Your book kind of interdisperses stoichiometry throughout the whole chapter as it talks about different categories of reactions. since there's really a lot of overlap there and the concepts are all the same, I think it makes more sense to cover stoichiometry all together in chapter 6. So we're actually going to do that all at the end. So we will do things in a little bit out of order for chapter 6, which if you're trying to follow along closely with the book, you might notice that we're skipping some things. That's because at the end of this chapter, which will probably be towards next week or even the week after that, there's a lot in this. At the end, I'll have a whole section of a lecture, probably at least half of a lecture, that's just on stoichiometry of these types of reactions. And I'll cover all that at once to keep it sort of cohesive. All right, but first we need some definitions and concepts to start before we get in. Today, we're not really going to talk about the quantitative aspects too much. All right, so solution is sort of a synonym for a homogeneous mixture. So it's two or more components, but where you can't really tell just by looking at it that you have two components. It looks like a single substance, even though it's two things physically mixed together. So it's not a chemical compound with two things bonded to each other. It's a physical mixture of two or more substances. And because it's homogeneous, that means it's a single phase. You can't just tell by looking at it that you have multiple things mixed together. And usually when we describe something as a solution, it involves a liquid. Now, there are technically solid solutions, and the air that you breathe is technically a solution because it's a mixture of many different gases all together. But when we say the word solution, we commonly mean something that involves a liquid as the major component. So some examples of solutions that are occurring in our everyday life would be if you go to the beach, salt water is a solution. Salt and water, use more than one salt, but mostly sodium chloride and water mixed together. It just looks like water, of course, but it's two different things. Most beverages, although the fizzy bubbly ones, not really, because you can see the gas bubbles as a separate component of the mixture, but any other beverage, like a juice, for example, that looks like a single liquid but has many things in it would be a solution. As you said, air is a solution of gases, even though it's not commonly described as such, or since we live in Houston, gasoline, of course, is a solution. It's many different liquids all mixed together. Now, in a solution, we typically define things in terms of what's called solute and solvent. So the solute is the minor component. And it can be a little bit ambiguous for mixtures of liquids or mixtures of gases. But for our purposes, we're going to have some chemical substance or some mixture of chemical substances dissolved in water. And whatever is being dissolved is going to be the solute. So if you dissolve table salt in water to make salt water, the salt will be the solute. It's what's being dissolved in the water. All right. And then the solvent is the major component, which for our purposes is typically going to be water. And you can think of the solvent as the substance that does the dissolving. It's the one that dissolves the other things. Usually when you describe something as a solvent, it's a liquid. I mean, almost always. I wouldn't say it's common to describe anything else as a solvent, so it's typically a liquid. In this course, especially, it's going to be water, although it doesn't have to be. And then another term that goes along with this then is if you have a solution that's described as aqueous, that means that it's a solution that's dissolved in water. So a more proper term than salt water would be aqueous sodium chloride. You have sodium chloride dissolved in water, so we call it aqueous. So that's what that word means. All right, so those are some of the common terms that are associated with solutions. Now, in this course, as we said, in a lot of chemistry, not just this course, and anything with biologically related, especially, the main solvent you're going to be dealing with is water. Why is water good at dissolving things? Well, that stems from it being a polar substance. And so to understand why water dissolves a lot of different things, especially ionic compounds and acids and things, which are going to be the subject of this chapter, it really boils down to the polarity of water, which is something that we already kind of covered. So first recognize that in water, which is H2O, you have two elements, oxygen and hydrogen, and oxygen is the second most electronegative element on the periodic table, significantly more electronegative than hydrogen. So you have polar OH bonds in water. In addition to that, the shape of water is bent, which means that those bond dipoles don't cancel each other out. They reinforce each other in some ways. So this is, again, showing that in different ways, these last three diagrams here. This is called a space filling model where you have the hydrogen on the bottom, oxygen on the top. Red means that there's negative charge. Blue means there's positive charge. You can also indicate that with arrows or delta plus, delta minus designations, all the stuff that we talked about back in chapter 4. Just a little bit of a review. So what that leads to then is that water has negative and positive poles, as they're sometimes called. And again, that's kind of what's indicated here. You have the sort of negative end up there, partial positive charges at the bottom, and that creates a separation where it's negative on one side, positive on the other. So water is particularly good then at dissolving other substances that are polar or ionic, because the negative part of the water molecule can line up with the positive part of what it's dissolving and make a strong interaction with it, and vice versa. So now you can answer the age-old question that if a white bear and a brown bear jumped in the water at the same time, which one would dissolve first? The white bear, because it's polar, yes. Okay, so that's what means, why the polarity of water is important is that it's able to dissolve other things that are polar or ionic. So we want to understand that a little bit then at the microscopic level. I used to have a better video for this that I liked, but clearly it was old because it's on a website that I don't think exists anymore. So, but this simulation is pretty good too. And if you look back at some of my older recordings, you might see the old version of this as well. But basically, we want to start talking about what happens when something dissolves in water. And the first aspect of that is let's kind of look at, again, a microscopic level. What is the water molecules? What are they doing with whatever it's dissolving? And that's what this simulation kind of shows. Although again, not as well as I would hopefully like. Okay, so that's going to be. I hope that there was no like noise in the background from that. All right, so let's launch this. This is that same website where we had the simulations for VSCPR. Has some other ones, and this one's about dissolving things in water, if it works. All right. So there's a few there's like a few different things you can do with this. It has this really cheesy interface where you shake the salt shaker, and salt's supposed to go in the water. I don't see it going in though. Oh no. There it goes. So you can dissolve salt in water. I mean, that's what it looks like. Of course, that's dumb. But what's really more useful is if we go kind of at the microscopic level. So it has two different substances you can dissolve also. So water can dissolve ionic compounds very well in many cases, and it can dissolve other polar covalent compounds that are not water. So here's one that's sodium chloride. All right, so sodium chloride is a mixture of two ions that go into the water. And what you can see is sort of happening is that as they go into the water, the two ions separate from each other. So that's right. So you don't really have NaCl ionically bonded to itself anymore. The ions completely separate from each other as they get dissolved in water. That's the key thing to realize with ionic compounds dissolving in water. Now, if we take a covalent compound, sucrose, let's get rid of our salt and add sucrose. Sucrose is just table sugar. It's a polar covalent compound, but it's not ionic. And if we dissolve some of that, so sugar is made up of these large molecules here. It's like C12H22O11 is the formula. Now, when they go in water, the intermolecular forces between the sugar molecules are broken, but the molecules themselves stay together. You don't separate the molecule into ions or into different parts. Each molecule is still intact as it goes into solution. And then you can see that a little bit better here. Again, not as good as the previous one if you look really deeply at the microscopic level. So these are the water molecules. Red is oxygen, white is hydrogen. And so if we put salt into there, I gotta figure out how to do that. All right, if we put some salt into there, again, what you can see happening is the ions are separating. If you look really closely, the hydrogen atoms, which are positively charged, they line up with the negatively charged chloride, and then the oxygen atoms, which are partially negatively charged, line up with the positively charged sodium. So you're getting that sort of opposite charges lining up with each other. The partial negative on oxygen lines up with the sodium plus and surrounds it, and then the partial positive on the hydrogens in water line up with CO minus. But if we do it with sugar instead, again, what you can see at the microscopic level is the sugar molecules get separated and they have different types of intermolecular forces with water, hydrogen bonds and things that we talked about, or haven't really talked about yet, unfortunately, but we will in the future. I'm getting ahead of myself. But nonetheless, you can see that the molecules, the key part is that the sugar molecules, these big yellow blobs made up of a bunch of different atoms, they stay together. They don't get pulled apart or ionized in any way. So that's the key difference between dissolving ionic and covalent compounds. So when you dissolve ionic compounds, should I give myself a little bit more room here? When you dissolve ionic compounds, the ions separate in solution. So you don't have ionic bonds anymore between the ions. But then for covalent compounds dissolved in water, there's no bond breaking occurring within the molecule. The molecules stay together. They get separated by the water molecule. They have forces of attraction with the water, which we'll sort of talk about in more detail at the very end of this course. So it's not clear exactly how that works yet, but you're not breaking the compounds apart. The molecules are staying together. That's the key difference. Now, with that microscopic difference in mind, how does that then affect the properties of these solutions? That's something else that we also want to talk about. Remember, chemistry is the science that links the microscopic world to the macroscopic world. So what happens to the properties of those solutions as we go? So that's what this video here is going to show. And this guy is an absolute nutcase, but the video is still useful. So he's going to dissolve a bunch of different substances in water, and he's going to test whether or not they conduct electricity by lighting up a light bulb, okay? So here's just tap water, which has maybe a little bit of stuff dissolved in it, but you can see there's very little. The light bulb is very dim. If he goes to pure distilled water, nothing happens. So water itself doesn't conduct electricity. But here is sodium chloride, salt water. So you can see that when you have salt water dissolved in water, it conducts electricity really well. A strong acid, HCl, behaves very similarly. So again, suggesting that there's ions in solution. Another ionic compound, NaOH, technically a strong base, but one that is also ionic. Here's that sugar water, though. When the covalent compound is dissolved in water, you don't form ions. It doesn't conduct electricity as a result. Vinegar is a weak acid, acetic acid, so it conducts electricity, but not quite as well as we saw with the strong acid. And then here's another covalent compound, ethanol, which is drinking alcohol or rubbing alcohol. Sorry, rubbing alcohol is isopropanol. Don't do that. And then here's an ionic compound, barium sulfate, that is not soluble in water. So it mixes with water, but it doesn't dissolve. And you can see that when the ionic compound is not dissolved in water, no conductivity electricity occurs. And so what that means basically is when you have ions in solution, you conduct electricity because you're separating the ions and you have these free charges. Are you having a hard time understanding your instructor? That might be a question for you guys. All right, so but that's the key differences of solution properties that result again from the differences between dissolving and solution. So some key properties here: if you have ionic compounds or strong acids in solution that produce ions, anything that produces ions in solution, they conduct electricity. So the term that we use then for this is a solution that conducts electricity is called an electrolyte solution. Probably heard of electrolytes in the context of nutrition. In chemistry, it means something that produces ions in solution, so it would be one that conducts electricity. How much more do I have? I think this is towards the end, right? Yeah, almost done. All right, so anything that conducts electricity is an electrolyte solution. Now, within that, we have two subcategories: strong electrolytes, weak electrolytes. So, for a strong electrolyte solution, the compound dissolves in water and it completely separates into ions. And that's what we saw with sodium chloride, HCl. So, typically, strong electrolytes are going to be soluble ionic compounds. When you dissolve them in water, they completely separate into their individual ions. The positive ions and negative ions get pulled apart by the water. Or you can have strong acid that are classified as strong electrolytes as well. We'll talk a lot more about the behavior of acids in this chapter, but basically an acid, as we talked about in chapter 3, is a substance that starts with hydrogen and is paired with some anion, and they behave in some ways like ionic compounds. When you dissolve in water, they get pulled apart into H plus ions, which are the hydrogen ions, or hydronium as they're called in water, and the anion. But there's strong acids are going to be the ones that you should know are HCl, HNO3, H2SO4, or HClO4 for chloric acid. There's more strong acids than this. We'll give a more comprehensive list later, but not too many more, and those are some of the common ones. And the key thing is when these dissolve in water, they conduct electricity really well. We also have weak electrolyte solutions. So these are solutions that would produce ions in solution, but the compound doesn't completely break down into ions. It's going to release some ions in solution, but a lot of the molecules are going to be intact. And that, for our purposes, is going to basically just be weak acids and weak bases. As I said, we'll have a lot more detail about acid-base chemistry later on in this chapter, and how it works. But when you dissolve these in water, they partially break down into ions, I should say, and they weakly conduct electricity as a result. So there's some ions in solution, so you get some conductivity, but they don't conduct as strongly because there's not as many ions in solution. A lot of the molecules are still intact. I should also add HBr and HI up here, so if I want to be complete. Um, again, that's coming back, so don't worry about memorizing it too much right now. But then we have weak acids fall into this category. That would be all other acids besides the ones I've listed above. We can assume are weak acids that we see in this course, or weak bases, but the only weak bases that you have to worry about is ammonia and H3. Again, more details coming on that. But those are the compounds that are weak electrolytes. You dissolve them in water, they partially separate into ions, but they don't completely break apart, so the conductivity is not as strong. And then finally, as we also saw in the video, you can have some solutions that don't conduct electricity at all. So when sugar was dissolved in water, or ethanol or any other alcohol is dissolved in water, you don't see any. And those are called non-electrolyte solutions. They have no electrical conductivity. And that's what you would observe when a covalent compound that is not an acid or a base is dissolved in water. So a regular covalent compound, but one that's not classified as an acid or a base. As I said, sugar is a common one that you'll see in a general chemistry course, alcohols. And then one key distinction I want to make, just because it causes confusion in this part of the course, if you have something that ends in COOH, that's going to typically be a weak acid. So if it has OOH at the end, two oxygens with an OH on them, technically, that's a weak acid. Like acetic acid will be one of them, the one that you guys would be familiar with already. And then if it just ends in OH, so there's only a single oxygen atom, this is going to be an alcohol, and it's going to be a non-electrolyte. So make sure you keep those straight because they look kind of similar, some of the formulas for those. they both end in OH, but if it's two oxygens with when one of them has an OH on it, then that's classified as a weak acid. If it's just OH by itself, that would be an alcohol. All right, we do have a quick announcement. Before that, I forgot what this was about already, but
Yeah. Hey, everybody, super fast before you guys leave. My name is Jordan. I'm with Special Events. Before you tell the student activities each term, look for fun, inexpensive things for us to do outside class. Something that we had done before that was popular, we decided again, is I got an allotment of student faculty athletes to go play paintball at a place called